All right, team, let's get started. As your chief systems engineer, I wanted to bring everyone in on what I think is one of the most fascinating projects in the entire automotive industry right now. And no, we're not talking about some $1 million hypercar or a fancy 800-volt sedan. We're diving into a real high-stakes engineering challenge where every single penny, every single component choice matters. Our mission? To design the brain for the people's electric car. Let's get into it. Just look at these. You've got the Wuling Mini EV, the Citroën Ami, the Nissan Sakura. These aren't just cars, you know? They are a full-blown revolution on wheels. We call them micro low-speed electric vehicles, or LSEVs, and they are completely rewriting the rules for city driving for millions of people. They're cheap, they're efficient, and they're just perfect for urban life. This is a fundamental shift in what a car can even be. But here's the kicker. Tucked away inside these tiny vehicles is a massive engineering puzzle. How on earth do you design and build a battery system, the very heart of the car, that is tough, dependable, and above all, safe, when your entire budget is just a tiny fraction of what goes into a high-end EV? Well, the answer is in its brain, the battery management system, the BMS. And designing that brain from the ground up, that is our job. Okay, so here's the mission briefing, plain and simple. We are tasked with creating the complete engineering blueprint for a truly world-class battery management system. Our job is to walk this razor's edge between extreme, and I mean extreme, cost pressure and the absolutely non-negotiable demands of global safety standards. This is where smart, elegant engineering makes all the difference. Now, before we sketch a single circuit or write one line of code, we have to know the rules of the game. We're designing a global platform, right? So our BMS has to be a master of compliance. It needs to satisfy the safety regulations of the three biggest markets out there: China, Europe, and the United States. And let me be clear, these aren't suggestions. These are the hard boundaries of our sandbox. And as you can see here, the priorities are wildly different depending on where you are. Just look at China's new GB 38031 standard. It's zero tolerance for thermal runaway. That means no fire, no explosion. Full stop. It's a game changer. Then you've got Europe. Their ECE R136 standard for these little L category vehicles is obsessed with high-intensity vibration. Because let's face it, these cars have simple suspensions and that battery pack is going to get shaken around. And the US, they are laser-focused on post-crash safety, making sure that high voltage is contained and safe literally seconds after an impact. Our design has to do it all. This quote right here, it perfectly sums up the massive shift in China's new standard. It is a complete 180 in philosophy. The old way was, okay, give the driver a warning so they have time to get out. The new way demands that our BMS is smart enough to predict and prevent a fire from ever happening in the first place. This means we have to move from just passive monitoring to truly active, predictive safety. So the takeaway is huge. Our BMS can't just be a watchdog anymore. It has to be a fortune teller. Okay, so with those rules firmly in mind, we arrive at our first and, frankly, our single most important architectural decision, the system voltage. This choice, this one choice, will ripple through everything that follows. It'll dictate our component costs, the thickness of our wires, the car's overall efficiency. It is the bedrock of our entire design. And it really just comes down to some simple physics. You know, power equals voltage times current. So for the same 20 kilowatt motor, if we double the voltage from, say, 48 to 96 volts, we cut the current in half. It's that simple. And half the current means we can use much smaller, lighter, and, this is key, cheaper copper cables. But even more important, it slashes the amount of energy we waste as heat. Heat loss is tied directly to current. So half the current means way, way less wasted energy. That efficiency is everything. And this is exactly why the 96 to 115 volt range is our strategic sweet spot. It's the Goldilocks zone. It's high enough to give us all those huge efficiency benefits, but it's still low enough that we can use affordable, mass-produced 150-volt industrial components. We get to avoid that massive price jump to the fancy, specialized silicon carbide electronics that you absolutely need for the 400-volt systems in bigger EVs. I mean, the Wuling Mini EV proved that this is the architecture that wins on cost and scale. Okay, great. Our architecture is locked in. 96 volts it is. So now, how do we actually build the brain itself? How do we pack the absolute highest levels of safety into this system without totally blowing our microcar budget? Well, the answer isn't about using the most expensive parts. It's about using the right parts and using them smartly. Our hardware strategy follows one simple rule. Keep it simple. First, the topology has to be centralized. All the intelligence lives on one single circuit board. That immediately gets rid of the cost and all the complexity of the master-slave setups you see in bigger battery packs. For a microcontroller, the MCU, we'll go with a cost-optimized chip, like a GigaDevice GD32. And to sense current, we're using a high-precision shunt resistor. For our needs, it's actually more accurate and way cheaper than a Hall effect sensor. Simple, effective, and it keeps the cost down. Now, let me show you our secret weapon for achieving affordable safety. It's a concept called ASIL decomposition. It sounds a little technical, but it's an incredibly elegant idea from the world of functional safety. Basically, instead of using one super expensive, super complex system to hit the highest safety level, which is called ASIL D, you can use two simpler, cheaper, and totally independent systems that each only have to meet a lower safety level, ASIL B. Let me just walk you through how this works. Our big goal is to prevent a battery overcharge. That's a critical ASIL D level risk. So path A is our main microcontroller, our primary brain. It's an ASIL B system, it watches the voltage, and it can open the main switches. But we add path B, a completely separate, simple little protection chip. It's also rated ASIL B, and it does only one thing, it watches the voltage. So if our main brain has a software glitch or fails for some reason, this independent backup is still there and can cut the power. Together, those two ASIL B paths give us an ASIL D safety rating. It's brilliant, really. So, we've defined our architecture, we've picked our hardware, and we have our safety strategy. But there is one last final hurdle we absolutely have to clear to make sure these cars are a success in the real world. And it's a problem that actually happens outside the car, but has to be solved from within. You see, the biggest problem isn't the car, it's the plug. All those public DC fast chargers out there, they were all built for big 400-volt or 800-volt EVs. So what do you think happens when our little 96-volt car pulls up to one of those high-voltage chargers? The short answer is nothing. They can't even talk to each other. The issue is a fundamental voltage mismatch. A public charger's minimum output voltage is often 200 volts, maybe even higher. It physically cannot step its voltage down low enough to safely charge our 96-volt battery. It's like trying to fill a water bottle with a fire hose. If we don't solve this, our cars would be completely locked out of the entire public fast charging network. And this is where the solution is, another beautiful piece of engineering. We integrate an onboard boost converter. Now, this is a really clever system that uses hardware we already have in the car's own motor and inverter, to temporarily act as a voltage booster. It literally raises our car's system voltage up to match the chargers, allowing them to shake hands and start charging. We solved a massive infrastructure problem without adding a bunch of expensive new parts. So, this is it. This is our blueprint for success. Number one, we lock in the 96-volt LFP architecture. It is the absolute sweet spot for cost and efficiency. Number two, we use that simple centralized topology combined with ASIL decomposition. That gives us maximum safety for minimum cost. Three, we leverage the mature global supply chain. And finally, number four, we design our system for boost charging right from day one, making sure this vehicle actually works in the real world. And that really brings us to the core philosophy of this whole project. For micro-EVs, success isn't about over-engineering. It's not about using the most expensive, highest-performance components you can find. It's about a relentless, obsessive focus on intelligent integration. It's about using the right parts smartly to deliver a product that is safe, that is reliable, and that is accessible to absolutely everyone. That is how we win.